On the back that we're going to learn today. Concentration. Find it. So very back. Use the word concentration. There's two equations next to it. What are they? Shelby, go ahead, read them. Molarity and parts per million. We'll talk about them today. We're going to learn how to use molarity today. That's what this worksheet is on. This is easy. A little bit harder on the back. But before we get to that, there's one thing I want to talk about first. I'm going to write a question down. You write it down in your notes and think about it. Does the solubility of NaCl solid, so let me write the big C there, of NaCl solid change if you dissolve a 10-gram, we'll say chunk of NaCl, or 10 grams of granulated NaCl. So does the solubility of NaCl change if you dissolve a 10-gram chunk of NaCl or 10 grams of granulated, meaning kind of like a powder, right? So granulated powder is kind of the same thing. And let's assume both the 10-gram chunk and 10 grams of the powder, the granulated, are being dissolved in 100 milliliters of H2O at 25 degrees Celsius. So both of those are the same conditions. So you have one beaker with 100 milliliters, one beaker with 100 milliliters. I used to have two, but one was spilled yesterday or the other day. So let's say these both have the same amount of water. Temperature is 25 for both. So the conditions are the same. One beaker, you drop a 10-gram chunk of the NaCl, like a big piece of it. And then this is just like, kind of looks like this, okay? Granulated, like the stuff you put on your food or whatever. So the question is, does the solubility change? Because we know if we change temperature and pressure, solubilities can change. What about if we change the way it's dissolved, like one big chunk or in little tiny pieces? What do you guys think?
Yeah.
I hear a yes.
Because.
What is? Let's before you say because, let's read the definition of solubility. Someone flip back on their notes. Read it to the class. Who's it going to be? Evan. Take pretty good notes, I think. Go back till you get to solubility. It's right in the beginning of the solutions notes. Should be a definition of solubility.
The amount of a substance that can dissolve in a given quantity of solvent at a specific temperature.
Right. Even though we know it, it still sounds confusing. So good job. So a certain amount of a solute, like NaCl, dissolved in a certain amount of solvent at a certain temperature. So solubility changes, I'm going to say this again, listen carefully, don't zone out on me, pay attention. Solubility changes if you change the amount of solute or the amount of water or the temperature. So you have to change one of those three. So, read the question again. Does the solubility change? Kristen.
Yeah.
Okay,
It's
why?
not now. Because there's more surface area if it's granulated.
Ah, very good. Surface area is the key here. However, solubility actually doesn't change. But what she's thinking is correct. She's just mixing the two concepts. So, solubility is how much we can dissolve, right? That's really what that means. Since we're dissolving the same amount.
It's the time that we have.
Right. What she's thinking is how fast it dissolves. What's that called? What's a fancy way to say how fast it dissolves? Speed. Good. There's another word. Starts with an R. Rate. So I want you guys to put a little star here. The rate. The rate of dissolving changes. The rate of dissolving is different, but the solubility stays the same. So the answer to this question is no. Solubility does not change. What does change? The rate of dissolving. So, surface area. If we have a big chunk of salt versus powder or granulated, okay? This has a higher surface area. Why? More pieces exposed to the environment, right? You guys remember when I poured the little pieces of zinc in that container, poured the acid and bubbled it through the water, and then lit it on fire? If I used one big chunk of zinc, it wouldn't have worked as well. Would not have produced as much hydrogen gas. So I use those little zinc pellets because anytime surface area is higher, things dissolve better, things react better. So surface area changes a lot of things. This is a physical process, but it dissolves a lot faster if you have little pieces. Or stir it up. If you ever want to make something dissolve faster, you guys do this. Coffee, hot chocolate, tea, or whatever. Anything you put, something, sugar, salt, anything you want to dissolve, you naturally just stir it. That's what people do. What are you doing? You're increasing the surface area. That's what you're doing. So it dissolves faster. So the rate of dissolving is different. The higher the surface area, equals increased rate of dissolving. I know I'm getting down at the bottom here, but so basically that means it dissolves faster. So I like to bring this question up because like Kristen there, she knew everything, but just got it a little bit confused, but that's okay, because that's normal. That's a normal thing for students to say. That's why I'm talking about it. So just be careful with that. You understand what solubility means, you understand what dissolving means, there's a difference. So it dissolves faster, but not necessarily more. So in other words, I can't dissolve more of the granulated. I can dissolve the same amount of both, right? In terms of the mass, this just dissolves faster. So that's the difference. Okay, I'd like to make that very clear because the regents will try and trick you on that. Questions? So now we gotta wait for you to copy it down.
I got it.
All right, so now concentration is where we're headed. We got a decent amount of time, so we should have time to get through the tough questions, so you should have no problem with 8, 9, and 10. We'll see. All right, so if I say concentration, what does that mean to you guys?
Isn't that the name of the game?
Of a game?
It's like this, and then you talk, and you have to.
What is it? Explain again. Concentration.
What do you do?
Yeah, what do you do?
You let go of someone, and then you have to.
Let me get this on
No.
camera first. Oh, I am recording. I forgot how you started.
Yeah, so what's concentration though? Are you talking about like concentration with your mind? I think that's what you're talking about. Concentration with your mind.
Yeah, but
Focus.
it's like a game.
Yeah, it's like focus.
Like,
But that's
you
different
know,
than concentration of like a liquid.
elementary school, and then
Right.
concentration is like how
Yeah.
Right.
It's
So,
two
so
different-
what about
How
here?
much
So, like,
solute
if you
is
put-
in a solution?
if you put
Right.
like lemon and lemonade.
And if it's concentrated, there's
What are you talking
a lot of it.
Right.
Concentration, you can
Here we
put
go.
lemon-
This is a lot of solute. Little
Like
bit
the
of
juice
solvent.
pack things that you're talking about.
Right, yes. If we pour this in here, it would be pretty concentrated because there's a lot of solute. But if we use less, that would be less concentrated or dilute. This would be concentrated, the other one would be dilute. So it's all about what?
You just pour it in.
Nope.
Yeah, I really
Why
want to
not?
see that.
So it's all about the ratio. So are you done here?
Mhm.
It's all about ratios. So give me a second. Yeah, and Jake, when I was talking about that earlier,
The frozen thing.
the frozen thing. Yeah, if you make juice from the frozen concentrate, it's called. You know, that sludge stuff that comes out of that
Yeah.
thing.
Eating like snow cone.
The tube.
Right, this kid eats them like snow cones. Right. Then after his whole thing, he said, "I'm just kidding, I don't do that." So yeah,
After 5 minutes of rambling.
that's very concentrated. You have to add water to dilute it. So let's write this down. Concentration. It's another way to talk about solubility. Okay, concentration. If you look at table T, like I said on the back, there's two types of concentration, and we'll talk about that, molarity and parts per million. But really, it's all about a ratio between solute and solvent. That's what it's all about. Okay, it's a ratio. So if you look at the equations for molarity and parts per million, the molarity formula is molarity equals moles of solute over liters of solution. Parts per million is parts per million. So if you're looking, as I'm saying, let's look at your reference table. So parts per million is grams or mass of solute over mass of solution times a million, right? Or is it grams? What word do they use? Mass or grams? Mass. Okay. Both of them have division. Look up here. That's what ratio is, right? Like 1 to 2, 1 over 2. So that's what concentration is all about. It's how much of this stuff, your solute, and how much of the solvent. So the two types we talk about are molarity and parts per million. Write this down. Molarity and parts per million. ppm, which is parts per million. So let me explain a little bit about where this stuff would be used in life. Molarity, basically just labs. I mean, plenty of people would have to know molarity for their jobs if they work at some sort of chemical company or, you guys ever hear of BASF?
Nope.
So the place is connected.
That's GE, but just use
No,
GE.
no.
GE,
I was thinking of something totally different.
there's definitely people that,
Isn't there a place that makes like computer chips?
I thought there
yes,
That's what the place you're talking about, right?
no.
Global.
Let's focus at GE. Okay, so people have, so I'm sure there's chemists at GE that have to know molarity. So molarity is really just a lab thing. It tells you how strong a solution is, weak or strong. Parts per million is more like real life. People that work for maybe the EPA. What's that?
The epidemic
Environmental
Protection
protection
Agency, right.
agency, yeah.
So I'm sure, I hope everyone has heard of the Flint, Michigan disaster.
Yeah.
Okay, with the water. So they want to save money, so they start using.
PFOAs, right?
What's that?
Is that the PFOA one or is that?
I'm talking about the water in Flint, Michigan.
Yeah, I know it.
No, it has.
Falls is one with
Hoosick Falls has some issues too right now.
PFOAs or something.
Oh, right, the actual chemical, I don't know what it is, but the lead in the water in the river there that they used was extremely high concentration. So it is a common term, educated people should know what it means. The EPA might take a sample of that water and they give you a number. The lead concentration is 25 ppm. So 25 parts per million, which is really high, it's a really high number. So if you look at the equation for parts per million, it means basically you have 25 grams of lead in 25 million grams of solution. That's kind of what that means. May not sound like a lot to you, but it's lead, so that's a lot. I would guess lead's concentration probably should be somewhere like 1 ppm or less. So I don't know what Flint's was, but it's obviously very high. So I'm just giving you an example, something kind of current, where that's probably used. Someone did some sort of test, and that's a unit they would put on their measurement. They wouldn't use molarity because that wouldn't really make much sense. So this one is more applicable to real life, I would say. You need to know how to do both for regents. And I think just hearing me say this and reading about it, there's some questions I'm going to give you. It just helps you be a little more educated. So anyways, we're going to learn how to use both of them this next week. This one we're going to learn today. So let's start with molarity. So for molarity, put a little star here. Let me make sure you understand what the numbers mean. If we have a highly concentrated, so a high concentration, that would equal something like 12 mHCl. Capital M means molarity. But the way you actually say this, the way you read this, is 12 molar HCl, M-O-L, oops, A-R, kind of like in your teeth, your mouth, teeth, molars, same pronunciation there. 12 molar HCl, that's how we would say that. 12 molar HCl solution. That would be concentrated. If you guys have ever seen me get acid from the back, it's in like a little, almost like octagon styrofoam container. There's a glass container that has like a little handle that I grab. Anyone ever seen me with that back there? Yes, no, maybe. Anyways, that's 12 molar HCl. I can show you. It comes in a special glass because that's really strong. So it can eat through normal glass, so they have a special type of glass. So what am I trying to get you to understand? 12 is a big number. A molarity of 12 is a big number. Okay, so something that is a low concentration or weak concentration might be 1. So low concentration would be 1 molar HCl. that's like what you guys would use in lab. I would take 12 and dilute it to 1 so no one's melting their face off. All right, because that's wouldn't melt your face off and being dramatic, but it can burn your skin pretty bad. So why am I telling you this? 12 means high, 1 means low. Just in general, you should have a concept of what the numbers mean. A lot of times we'll deal with less than 1 too. 0.5, 0.25. Questions? If you need a calculator,
It's gotta be.
now's the time to come up and get it. When I get back up here, we're going to do some practice problems using the molarity formula.
Hey, Jake.
Oh, hey. Oh, yeah, sure. Yeah. Devin, after class, you see Miss Landry? All right, here we go. All right, so I'm not really teaching you how to use the formula. I'm going to say you should know how to, because it's just algebra. Who likes algebra? Everybody?
Can you please? Can we please stop?
Garen Morin loves.
Fox loves algebra.
I just don't like
He
this.
loves it so much he took it twice.
Okay. Moles over liters. Now, if you look at the equation on the back of your reference tables, moles of solute divided by liters of solution. I just abbreviate moles and liters. I don't put the solute in solution. It's on your reference table, so you don't need to write it twice, but really it's just moles over liters. We know what moles are, right? It's a certain amount of something, and liters are volume. So I'm going to give you a pretty easy question to start us off, and then we'll get into some harder ones. So here we go. Write this down and solve it. Calculate the molarity of a solution, S-O-L-N is solution, by the way, of a solution containing I don't know, 1.5 moles of NaCl dissolved in 500.00 milliliters of solution. And yes, 500.00 needs to be written down because here's my here are my rules. Show your work, label your unit, and round to the proper number of sig figs. Show your work, label units, round to the proper number of sig figs. So you can't just write an answer down without a unit. I need to see, plug the numbers in the equation, show some work. You're solving for this right here. So it's pretty simple, this problem. You're solving for molarity, the capital M. But I want to see work, I want to see a unit, and I want to see correct number of sig figs. So I'll give you a couple minutes. We'll walk around and check it out. Yeah, good review for the sig figs.
So we're solving for.
Molarity.
Oh, so you just use that. Is this supposed to be hard?
No.
Okay.
However, there is a trick.
I don't like tricks.
I didn't go with my idea for April Fool's Day.
Yeah, I thought
I didn't have time. I was too
What was
busy.
your
I didn't really have time to put it together. I was going to give you guys a regents exam. Say, oh, by the way, you have a regents exam today. The grade will count, and I'm going to be real super serious about it. Give you about 5 minutes, and then once you're done sweating, I would say, I was just kidding. But I didn't know.
See, Bentley isn't here. and
That
I'm
is
happy
really
because
lame that you didn't do
I'm
that because that would have been like a
surprised
real
That would have.
decent memory for the 10th grade
I
year.
just didn't have time to get it together.
Hey, that would have been bad for the environment because you would have to print it out.
No, I have copies. I just didn't get it together. All right.
If you do it, you should. You know what you should do
It's over.
during your study hall class. You should make everyone have to do something stupid.
No, I
Because
can
you're gonna know it's a
actually instead of